Next, it's really the kind of roadmap presentation where we tell you about what DDN has been doing and has recently announced and will be doing in the next year, 2 years. My picture's on there, my name's on there, but I'm actually, I've got Sven here as well, and his picture's just here on his face. And he's called Sven and he's the CTO of DDN, and he'll be just helping me with some fun bits as we go through. Okay, we're nearly here.
He does all the work, I have all the fun.
And I write all the slides. So.
Right.
So I guess, firstly, you heard from NVIDIA. We started with NVIDIA 3.5 or 4 years ago when we delivered a, I guess, reasonably modest size, I think 10 systems initially to NVIDIA to support their Selene supercomputer. That was one Mark was mentioning. They really struggled to begin with their performance, and we came along with our A3i exascaler product and kind of took those problems off the table. And really the reason NVIDIA has stuck with us is because, yes, of course, performance, yes, of course, scale, but really it's efficiency. What they care about is the productive work they get out of their capital investment and their power investment and their people investment in these extremely large systems. That's what we're really good at. And you'll see a few times, and it is kind of marketing, and it's not marketing. But marketing, we've got a simple number, 10x. Why do we say 10x? Well, actually, we're talking about, let's say, productivity per something. So throughput per watt, throughput per rack unit, throughput per dollar, IOPS per dollar, all these metrics. And if we actually compare ourselves to our most vocal competitor, actually the numbers are multiple fold of that. We're like close to 40x in terms of writes per U than one of our competitors. We're 30x in terms of IOPS per rack unit versus a leading competitor of ours. So 10x is actually a rather modest statement. It sounds like a big claim, but actually when we look at the details ourselves, we find it's a relatively modest claim. So Jensen has been talking about accelerated computing for a while, and he actually states quite vocally what DDN have been doing and really has been the heart of the business for 20 years. It's doing more with less, getting more throughput, more IOPS, more data storage out as small a package as possible in terms of CPUs, in terms of DIMMs, in terms of cables, in terms of bits and pieces. Less for you to manage, faster applications is basically the essence of it. And we get there in a number of ways, which I'll talk about in the next slide. But the one way we'll be doing directly with NVIDIA is taking this quite complex stack, starting at AI frameworks, ending at an SSD, and all the things in between, and putting in linkages between these things, putting in optimizations that cross this stack. We can come up with many, many examples. We can talk about mmap IO, so making these AI applications go faster by serving the type of data they're asking for in a faster way. We implemented something called hot nodes about 2 years ago at NVIDIA, and that basically allows you to cache data in the DGX SSDs, and that gave them a 3% speed up. It sounds like nothing, right? It's not much 3%. But this is 3% of like a megawatt data center and the total throughput of the whole applications. By switching on one feature, they can save hundreds of thousands of pounds a year. So big stuff. And it's really about this stack integration we'll be doing a lot of.
GPU Direct is another example where we done optimizations with them. Yeah.
We'd like to talk about simplicity a lot more now. So I'll ask Sven, actually, to take you through what we've done around SFA in the past 2 years, because we've really spent kind of like 80% of the engineering effort has been simplifying that stuff over the past 3 years.
Yeah, so we saw that in the field. We got lots of feedback from customers that the stuff is just too hard to manage, particularly at large scale. Upgrades take far too long. We need to improve on that. And so as James just said, we basically asked the engineering team to refocus on making this significantly easier. And as always, if you put a very significant focus on it, good things come out of it. So these days, an upgrade of an SFA system can be done basically online on pretty much all aspects. The upgrades go very, very fast. It's all automated. Instead of going through hundreds of pages of instructions, there's a very, very small set of things that need to be done. And we're still not done with it. We've done a lot of work on the exascaler, the file system layer, integrating that more tightly from a management perspective with the hardware as well. And with our upcoming 6.3 release, there's going to be lots of really great stuff showing up there as well.
And so that's the SFA layer and the exascaler layer with exascaler management framework. Again, a big project from the exascaler team to orchestrate the coordination of upgrades and updates and management of the system in a much simpler way than was possible before. And it all gets exposed to end users if they choose to do so through Insight. And you'll see here the latest version of Insight. We've got physical real views allowing to pinpoint in large infrastructure where the problems are very, very quickly. And that all connects in back to our call home infrastructure where we have cloud analytics running against your logs to help us identify things quicker. We've done a huge amount in the past 3 years right across the stack to make this whole thing simpler. If we look at this little picture here, I'll just play it. I think it plays. So if you watch this little screen here, this is just a little snippet of very cool feature we have based on Lustre job stats. What it means is when that user calls you up and says, why is my job slow? You know, the first thing in the back of the administrator's mind is it's probably slow because somebody else is doing something bad to the file system. They're creating billions of files in a directory or doing something like this. And now, just by using this simple GUI, you can immediately go to that and find out who's doing what to the file system. And it'll tell you which job, which user is consuming your throughput, IOPS, or metadata. But this is really what it's about today. We're really talking about efficiency. That is, what are those ratios like in terms of performance per thing, where thing is rack unit, dollar, or watt consumed. And these basic numbers, if you look at those and compare us on a bit of paper with any of our competitors, you'll see this sort of 10x and more becoming very roundly obvious. In 2 rack units and 2 kilowatts, we're delivering 90 gigabytes a second for reads, 65 for writes, over 3.5 million IOPS actually, it's gone up from 3, and 720 terabytes of TLC capacity in just that thing there, just that. All you need is that, some cables to plug into your network, and you've got a complete parallel file system. Absolutely unique. Mind yourself about other architectures which are kind of more SAN-like with extended infrastructure at the back end, extended switching. We don't need that because we're a parallel file system. And really, we've seen this slide before, but nobody's really gone through it. But I wanted to take you through a few of the nuggets of why we're so efficient compared to particularly scale-out NASers. The first one is a thing we've been doing for the past 10 years, is taking what used to be, and actually even for us it used to be 10 years ago, a majority was this, is a pile of servers, some cables, connected to some storage, et cetera, et cetera. And we've collapsed that down into these virtualized platforms over a period of 10 years, and every basically CPU cycle, every new CPU generation, this has got more and more effective as we can pack more of the services in without loss of performance. Now, literally everything we ship is virtualized like this. We've shipped maybe one system with external servers in the past sort of 6 months, something like that. So it's all virtualized. And that means much more efficiency gains for you. We're going to talk about QLC. Who knows what QLC is? I'm not expecting everybody to put their hands up. QLC, put your hands up. Put your hands up if you don't. That would be fine too, no problem. Okay. So we're going to talk about QLC in a minute. What I'll tell you now is that these are large capacity drives. Large capacity drives means more for your money, more for your watts, more for your rack units. And the story goes on. I could spend half an hour talking about this, but really the middle one is one of the key architectural differences between ourselves and a scale-out NAS. By having an intelligent client which knows where the data is, we effectively double the efficiency of the entire architecture because the servers don't have to go and retrieve your data from somewhere. Clients get it direct. And that's really the magic of the scalability of a parallel file system is right in that. It's the fact that clients know where the data is and they can go and get it directly. That takes away the back-end network, the back-end SAN-like infrastructure, and it allows us to scale much more simply. I should also mention the workload focus. We do a lot of work making sure applications go faster. Whilst we do talk about storage performance figures, and customers like us to talk about that, and that's how we get compared. Actually, what really matters is, does your application go faster when you install our storage? And often, even if a storage system says it does a terabyte a second, an individual application might not be able to see that because it's all about protocols. It's all about supporting particular kinds of I/O patterns, moving data into a single thread on a particular client architecture. We really go the extra mile there to make sure applications see speed up. So the big slide. We're now launching, and I'll give you 2 more slides to go into a bit more detail, 2 new elements that are going to dramatically improve the cost and efficiency of our systems. starting from Q3 and Q4 this year. It comes with Exascaler 6.3, the next major release, and it includes two things. One at the top there is data reduction. So at the client side, we've plugged into kernel level compression, and we'll compress that data before it hits the wire. Secondly, we've implemented a brand new NVMe over Fabrics network behind our controller systems to allow us to expand the flash footprint using low-cost QLC. Now, just one sentence of explanation for what QLC is, because there was a couple of hands there. TLC is the generation of flash which most people have been relying upon, which is quite expensive in terms of dollars per terabyte, but very, very fast. QLC came to the market originally about 2 years ago, and it really reduces this cost per terabyte by a factor of 2 or so. It does it at a small performance penalty, but still, it's still way, way beyond what HDD will deliver in terms of IOPS, in terms of throughput per device. So QLC gives us an ability to provide a bigger flash footprint at lower cost to customers with only a very small sacrifice in performance, if any. So we can then double the density of systems, we can increase the flash footprint, we can bring the price down, and we can maintain the performance. So let's go back into those two things, compression and QLC architectures. Firstly, compression. Now, the Exascaler team and Andreas and Peter and other Peter are all here, and you can talk to them through that conference. The Exascaler team, the Lustre team, have been developing this client-side compression. Essentially what we do is we leverage existing kernel integrations into various compression mechanisms. You just switch it on. It's super simple. If anybody's familiar with Lustre, LFS set stripe, new flag, you can apply it to a file system, you can apply it to a directory, you can apply it to a file, and then once on, that data it's going into destined for that directory, will become compressed as it moves through the Lustre client. And you can see here the compression ratios for different data set types, and the little blue bars there are some indicator of the minimal cost in CPU cycles as you do this compression on the compute side. And of course, it's a great way to do compression for two reasons. One, it scales infinitely because it scales with your compute. And B, we're compressing the data before it even hits the network. So if you do get 2 times compression, you're moving half the data across your network. So great infrastructure efficiency gains just by clicking that switch.
Or you can actually push twice the amount of data over the network, obviously. Yeah.
So let's have a little bit of a closer look at this QLC infrastructure. So we think, even though there's been QLC storage out there now for 2 years, they've really vastly underserved your applications and your workloads through being built into a tiered or inefficient architecture. By taking the parallel file system principles and DDN's architecture, we're literally able to get 10x more out of it. 10x in terms of IOPS, 10x in terms of throughput, and to keep those latencies small. Because we're not tiering anymore. We're really filtering. We're talking directly to QLC, we're leveraging the mass of QLC and writing to it directly, but we're filtering out small stuff, like metadata bits and pieces, journaling bits and pieces. We can take that out and put it in the TLC layer. So it's not tiering, we're not bottlenecked through a small little avenue of TLC or whatever it is. We're writing to this massive QLC, and that means you get the full benefit of IOPS, throughput, and read from all that QLC footprint. That's where we get this 10x improvement, and that's really why we think we've kind of resolved this challenge of getting performance out of QLC now. This one.
Go ahead.
So we've been shipping what's on the right and the left of this slide for maybe 2 years, roughly, 1.5 years, with various updates. The TLC flash is what we've shipped to 90% of SuperPods over the past 3.5 years. All those NVIDIA SuperPods really benefit from these systems. Completely scale out, completely simple, very easy building block based on our 400X2. The hybrid on the far side, that shows you the ideal optimal cost per terabyte, the best you can possibly get. We've absolutely reduced the costly controller piece, big, massive HDDs, excellent management from our SFA-OS layer. So we get the best price per terabyte with our hybrid systems. Small bit of TSC, lots of HDD. Now with this QLC option you see in the middle, we're mixing up TLC and QLC, and we can do so in different ratios. And if you look at the numbers with that system in the middle, we've got the best price for flash terabytes. The capacity has gone up per rack because we can use these big, dense devices, 60 terabyte devices, and we get extremely good throughputs and IOPS. And that's actually something we can tune. based on the system we want to create for you. So I'll show you a couple of examples of that in a couple of slides. So a little summary before we show a couple more examples. We're lowering cost by doing two things. We're using QLC and TLC, and we're adding compression, a very easy switch on the file system. We've got simpler scale, no back-end networking, no complex back-end infrastructure. Just take that building block, multiply, 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 multiply. And then thirdly, we continue, because we're DDN, to focus on applications, to optimize things like mmap, to provide things like intelligent caching so we can prefetch into your applications. We're focused on application performance because that's really what matters. And at the end of the day, that's why NVIDIA keeps going back to DDN for these large systems, because we scale. I'm going to pause there and ask for any questions, and then we're going to ask Sven to talk about something completely different. Thank you, Ron. You got a question there, Laurent? Question, Robert.
Sorry, I'll be difficult. Is the compression indexable? Do you have to start from the beginning?
Very good question. Where's Andreas?
So the question was whether you can do random I/O in a compressed file, and in fact, the data is compressed in like 64 or 1 megabyte or whatever chunk you can configure, and then you can do potentially random I/O on that. Of course, you would have to do it in a larger chunk size. So the minimum is 64K, but you can do larger. You get better compression ratio.
So most digital pathology and BAM-type genome files, they're already compressed and then indexed. So you might have to ask the users to turn all that off and leave the file system underneath.
Well, it's if they're already compressed, you're not going to get any benefit, and the algorithms will detect that they're compressed and stop trying to compress them, or you just don't turn it on in the first place.
Right.